Alright guys, so the next question, part A, says that to show that the sequence is between 0 and 1 when n is greater than or equal to 1. So the sequence is n factorial over 2 over 2n factorial. And we're saying it's between these bounds. Okay. Automatically this is true 100%, this is 0, because factorials have to be over 0 or positive no matter what. So we just gotta prove that it's less than 1. So what we could do with this, we can't really tell if it's always true right now because it's not simplified enough. So let's say we pull out one of these n factorials that's outside the bracket. We would have 1 times 2, and then we express one of the factorials all the way to n. And then if we did something to the bottom as well, the 2n, in fact, all of it factorial easily simplifies to n factorial n plus 1, n plus 2, dot, 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 all the way to 2n. So easily you can see here that these cancel out. And you're left with, if I separate these multiplied terms, get 1 over n plus 1 times 1 over 2 over n plus 2, dot, 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 n over 2n. And this is easily shown that it's less than 1. Try plugging in any value for n greater than or equal to 1, and you'll always get something less than 1. So that's shown right there. That's your answer. So part B says to use part A to determine if the following sequence converges or diverges. If it converges, find its limits. So it's asking us to use part A, which is it says whether or not you have shown it. So that means you're already given the information, even if you got part A wrong. So don't get part A wrong, anyways. So this is what we have from the original information, and this is our an n factorial squared over 2n plus 1. So we're going to have to use the squeeze theorem, and I'll get to what that is in a sec. So the missing term in this expression from here is 2n plus 1. So say I multiplied every side of this expression by 2n plus 1. So 0 times 2n plus 1 is 0 by 1 over 2n plus 1, right? So I would have 2n factorial, 2n plus 1 factorial, and this right side would be 1 over 2n plus 1 factorial. The squeeze theorem says that if you have, let's say we label this function, this left side f of x, this g of x, and this h of x. Squeeze theorem says that the limit as x approaches infinity of f of x, if it is the same as the limit of h of x as x approaches infinity, equals to some value L, then it automatically, g of x has the same limit. So if we can find both sides, each side, the limit on each side, and if it's the same, we automatically have the answer. Alright, so the limit on the left, on the f of x here, is automatically 0, right? On the right side, if you plug in infinity for n, you have a really large number at the bottom. So 1 over a big number is 0. So by squeeze theorem, L equals 0 for all three of those. And there's your answer. Alright guys, the next question is asking us to find if the following series converges or diverges, and if it converges, find its sum. Off the bat, you should be able to recognize this as a geometric series with the form a1 plus a1r plus a1r squared plus a1r cubed dot 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 all the way to a1r n minus 1. So we can see that if we compare, the constant is a1, and that's a constant right here, so a1 would be pi in this case. The next term is your a1 multiplied by r, so our a1 is pi, and it's multiplied by r, so r is automatically going to be negative 2 over e. Right? And in the case of geometric series, it converges if your the absolute value of r is less than 1. So the absolute value of negative 2 over e is 2 over e, and it is less than 1, so it converges. Of course it converges. That's what the question is. The question wants you to find its sum, so obviously they're going to make it convergent. And it's pretty easy to find in a geometric series where it converges to. You just do S is the sum, a over 1 minus r. So a1, so pi over 1 minus a negative 2 over e, so 1 plus 2 over e. If I multiply out this e to the denominator numerator, you get pi times e over e plus 2. So that's where it converges to. Alright guys, this is another easy one. You can see here that this is a partial infinite series because we have infinity over here. So for infinite series, we can find what it converges to by the expression limit as n approaches infinity of your Sn, and our Sn is given here, is equal to the limit as n approaches infinity, 3 minus n over 1 plus 2n equals. So to evaluate a limit at infinity, for something simple like this, if you just divide every single term by n, you'll get 3 over n minus 1 over 1 by n plus 2. And this is easy to see that this goes to 0, this goes to 0, so we're having negative 1/2. Alright guys, we're approaching the end, almost the end of the exam. This is the second last question. It's asking us to determine if each series is absolutely convergent, conditionally convergent, or divergent. Clearly states which test you're using for each problem. So our first series is ln of n over ln n squared plus 1. This looks very ideal for the divergence test because it's simply just taking the limit as n approaches infinity of a of n, which is our series, and if the answer is not 0, anything but 0, then we have divergence. Simple as that. So let's go ahead and take the limit as n approaches infinity of ln n over ln n squared plus 1. Remember from calculus 1, we can easily do L'Hopital's rule. L'Hopital's rule to further reduce this to something we can actually plug in infinity to. So this would equal the limit as n approaches infinity. Taking the derivative of the top, you have 1 over n. Taking the derivative of the bottom, we have 2n over n squared plus 1. And this further simplifies to 1 over n multiplied by n squared plus 1 over 2n. And finally, we just multiply in that 1 over n. We get n squared plus 1 over 2n squared. Here we can just divide everything by n squared, so we got 1 plus 1 over n squared over 2. If we plug in our infinity here, we get this term go to 0, so we just get 1 over half, and that's not equal to 0, so 100% it diverges. Alright guys, in this problem here, sorry that it went over there, hold on a second, I'll just fix it. Alright, in this problem, we have the summation from n equals 6 to infinity of 1 minus 5 over n to the power of n squared. You should be able to recognize that this is a great candidate for the root test, mostly because of this exponent variable squared. The root test states that L equals the limit as n approaches infinity of the root of our an, which is the series, the absolute value, and the nth root. It's the nth root. And that's further changed to 1 by n. So if I go ahead and plug in our series here, L equals the limit as n approaches infinity of the root of the absolute value of 1 minus 5 by n, like so, then in brackets to the n squared. And then I can put it in this form here. So it's the limit as n approaches infinity. So if I convert here, there's an n over here. So if I make this look like that, 1 over 5 over n. Now we have a 1 over n here, but we also have this n squared, right? So cancel out, and this we're just left with 1n on the top. So I'll rewrite it here. Limit n goes to infinity of 1 minus 5 by n to the n. Alright, so the thing here about the root test is that if the limit is less than 1, we get absolutely convergent. If it's e greater than 1, it's divergent. And if it's equal to 1, we can't really tell. It's maybe divergent, maybe divergent, absolutely convergent, or conditionally convergent. So we don't know really yet if we get L is equal to 1. So what we're working with here is L is equal to the limit n approaches infinity, 1 absolute value 1 over 5 over n to the n. Okay, so to solve these kinds of problems, we did one in Calculus 1. We would simply just take the ln on both sides, and we get ln L is equal to the limit n approaches infinity of ln, and we can drop these absolute value signs, 5 by n to the n. Alright, so this further changes to ln L. So you can bring this n to the front of the ln, and ln 1 minus 5 by n. And this further changes to ln 1 minus 5 by n over 1 over n. The limits here. Now if we put it in this form, we can now start applying L'Hopital's rule here to derive the top and bottom until we get something that makes sense with this infinity limit. So applying L'Hopital's rule, we get the limit as n approaches infinity of, so the numerator will be 1 over 1 minus 5 by n, and I have to multiply that 5 over n squared, negative 1 over n squared. That's deriving the denominator, and that change to the limit as n approaches infinity. So term-wise, Splitting this up, now we see that these cancel. So now if we plug in infinity here, we get 0 to this term. So we get 1 times 5 times 1 negative is equal to negative 5. So now that we've concluded that ln of L is equal to negative 5, so L is equal to e to the negative 5, right? And this is 1 over e to the 5. And is this less than 1 or greater than 1? It's less than 1. So by our definitions here, the root test proves that it's absolutely convergent. Alright guys, so the next part of this question, the last part, it says that the summation from n equals 2 to infinity of negative 1 to the power of n plus 1 times the square root of 1 over n squared minus 2. This should be obviously a split-second decision that this is an alternating series. It's the exact form of 1. This is the form of an alternating series. Negative 1 to the power of n plus 1 times some b of n, where b of n is greater than or equals 0 for all n. There's the conditions to determine whether it's convergent or divergent. We can tell if an alternating series is converging if the limit as n approaches infinity of bn is equal to 0. Bn in this case would be root 1 over n squared minus 2. And the second condition is the part bn is eventually a decreasing sequence. Then we know it converges. So let's test them out. So the limit as n approaches infinity of root 1 over n squared minus 2 is obviously a 1 over a very, very large number, so it's 0, so that's check mark. And Bn is eventually a decreasing sequence. To prove that, let's see if that our summation, let's say we make our summation one value higher, then our b of n would look like the following. N plus 1, so this is the next term, and this is the term before that term. So if this condition is satisfied, then we have a decreasing function. So let's say I plug in some value 5 here, you would get that 0.17 is less than 0.20. So it is decreasing. So this proves that it's converging here. But for alternating series, you have to also evaluate the absolute value of your series. So we have to find whether the absolute value of our series is diverging or converging. And the absolute value of our series here, this term would become positive. It's negative 1. So you're basically just evaluating b of n. Not all the time, but this time, yes. So 1 over root n squared minus 1, minus 2. We have to see if this is converging and diverging. So what we would do here is we do the direct comparison test. Now if I write our sequence here, n squared minus 2, there's a similar similar sequence to it that's just 1 over n squared, right? It's very similar, which is also equal to 1 over n, right? So if we see that this is diverging or converging, then this must also be diverging or converging by this inequality here, this equality here. So we know that this automatically diverges. It obviously does. So this must converge as well. Diverge, sorry. So we conclude that because A of n converges and absolute value of A of n diverges, we have conditional convergence. Alright, let's move on to the last question. Alright guys, we're at the last part of the exam. The question here says to find the interval of convergence of the power series, summation n equals 0 to infinity, all that. So to find interval of convergences for power series, we usually use the ratio test. The ratio test here states that we're finding the value L, where L is the limit as n approaches infinity of our power series A sub n plus 1 over A n. We'll fill that in soon. And if L is less than 1, it's absolutely convergent. If it's greater than 1, it's divergent. And if it's L equals 1, it may diverge or converge. So if we set up this this test here with our series, so A sub n plus 1 will mean that wherever there's an n, we'll just change it to n plus 1. So negative 1 to the n plus 1. So n here, n plus 1, the n changes to n plus 1, so we get n plus 2. X minus 3 to the n plus 1. And that's all over the original, just A of n. So negative 1 to the n plus 1, x minus 3 to the n, absolute value, and 10 to infinity. If you just subtract exponents here, because it's being divided, you just get left with n plus 2 over n plus 1 times x minus 3. That would be absolute value of x minus 3. It's very important. Which is just equal to, if we evaluate the limit here, we plug in, we divide everything in each term by n. You'll see that this 2 over n will go to 0, this 1 over n will go to 0. You'll just be left with 1 over 1, so your limit is x minus 3 absolute value. So, question's asking us for the interval of convergence, and it will only converge if L is less than 1, so x minus 3 has to be less than 1. And what we usually do is, in power series in interval test, we make it go from negative 1 to 1, and now we're going to isolate for, we'll bring over this 3 to adjust each side. So x has to be less than 4 and less than 2. So now what we do is we plug in each of these extremities into our original power series. So we get summation n equals 0. We have to find out if it diverges at this x value. Negative 1 to the n plus 1. So we got negative 1 in here, x minus 3 to the n. And that just equals summation n equals 0, n plus 1. And now, if we just evaluate this at the limit as n goes to infinity, we see that it will diverge. And now if we evaluate at x equals 4, we get the summation of n equals 0 to infinity, negative 1 to the n plus 1, 1, and negative 1 to the n plus 1. So this one as well will diverge if you set n to infinity. So because they both diverge at the bounds, x has to be less than 2 and x has to be less than 4 for it to converge. So the interval of convergence is from 2 to 4. Alright. Alright guys, part B is asking us to show that Taylor series for f of x 1 over x minus 2 squared centered at a equals 3 is equal to that. So we gotta go from that to that. Taylor series is of the form summation n equals 0 to infinity f of n to the power of n of a over n factorial x minus a to the n. So we can find each of these things here. This f of n is the nth derivative, a is your point that it's centered at, n factorial x minus a. So we have to determine a formula for f of n. So let's go ahead and see what f of 0 gives and see if we can come out of a pattern. F of 0 is just a function itself, so we'll bring the x minus 2 squared to the numerator, so we get x minus 2 to negative 2. So f prime, so f1, the first derivative, is equal to negative 2 x minus 2 to the negative 3, second derivative, 2 times 3 x minus 2 to the negative 4. And if we do one more time, we can deduce the general formula for this. And the general formula for the nth derivative, negative 1 to the n plus 1, x minus 2 to the negative n plus 2. So now if we evaluate our nth derivative at our point that we're centering it at, we would get, or we plug in for x, we plug in 3. We get negative 1 to the n plus 1 factorial times 1. This just becomes 1. So that's what we have right there. Now we have all we need to plug in for our Taylor series. Just do it here in green. Summation n equals 0. Ready. So it would be f of the nth derivative of 3 over n factorial x minus 3 to the n. So that is simply negative 1 to the n plus 1 factorial x minus 3 to the n all over n factorial. This n factorial will be cancelled out with the top factorial. So we're left with negative 1 to the n plus 1, x minus 3 to the n. Alright, let's move on to part. Alright guys, so part C is asking us to use A and B, part A and B, to show that the summation of n equals 0 to infinity of n plus 1 over 2 to the power n equals 4. The little hint they're giving us, that x is equal to 5 over 2, should lie in the interval of convergence. Our interval of convergence was the following, and 2.5 does lie inside this interval. So what we're going to be using to solve this problem is our original function given in part B, which is 1 over x minus 2 squared, and this Taylor series over here, summation n equals 0 what we're going to have to do to solve this problem is we're going to have to set these equal to each other and evaluate them at this point that they give you. All right, so let's go ahead and do that. So 1 over 5 by 2. Well, I put 2.5 here, but 5 by 2, same thing. Minus 2 squared and equals summation n equals 0 to infinity, negative 1 to the n plus 1, 5 over 2 minus 3, which will go to negative 1/2. So here, this whole expression becomes 4, and then we get to infinity, negative 1 to the n plus 1, negative 1/2 to the n. And we can easily see that this term here reduces to n plus 1 over 2n. Alright guys, that concludes the examination. Thank you for following along this journey. I really hope you guys are successful in your Calculus 2 course. If my video is not enough, there's plenty of resources on YouTube from other people on specific topics. So I guess I wish you guys the best of luck, and I'll probably be here for Cal 3 as well, where we do double and triple integrals, all that stuff. It's more fun actually, I'm not gonna lie. So guys, I'll see you guys in the next video.